Good morning, dear students. So today I'm going to continue with the design or the evaluation of settling velocity of a grid particles. How to estimate? So the question is, find the settling velocity of diameter 0.5 mm at 20 degrees centigrade. Since the question itself is for the grid particles, it will always give that the specific gravity is 2.65 and the dynamic viscosity of the fluid that is going to settle down, especially for the water in this water, the dynamic viscosity is around 1.002 into 10 to the power minus 3 Newton second per meter square. So question is very simple. A particle is settling down of a size 0.5 millimeter at ambient temperature of 20 degrees centigrade of the fluid. And the specific gravity of the solid is 2.65. If it's not 2.65, then it's not a type 1 particle. So it's not a discrete particle and this problem will not exist. And the dynamic viscosity of the such fluids where it is settling down is 1.002 into 10 to the power minus 3 Newton second per meter square. As simple as that, sometimes even you can mug it up this value because it's quite very common with almost all the fluids where we are dealing with water or wastewater treatment plant. Now listen, by using the formula, the calculation is very simple, but how to approach, how to start? We know that in settling velocity, number one, the terminal velocity equation is V settling square is equal to 4 by 3 G D S minus 1 divided by C D. This is the terminal velocity equation we have derived in the last class. Okay. And this can also be described as 4 by 3 G D is rho B minus rho W divided by rho W into CD. This is equation number 1 we have in common. Number 2 equation is, if the flow is supposed to be laminar, then by Stokes law, settling velocity is 1 by 18 GD square rho B minus rho W divided by dynamic viscosity. Correct? Now, the question comes, which equation are we supposed to use? From here, the problem will start solving. We are supposed to find the settling velocity. But here, if we use the equation first one, then we have to know the value of CD, correct? Let's assume that we are using this because we don't know what type of flow it is. So G we have, D we have, diameter we have, specific gravity only we have, CD is there. So what happened is, CD again, we said that it is 24 by Reynolds number if it is laminar, then it's equal to 24 by RE plus 3 by root over RE plus 0.34 if it is transitional. Okay. But the problem is, Reynolds number again is nothing. The velocity into the diameter into the density divided by dynamic viscosity. Correct? So if we want to use this equation, we should know what is the value of CD. CD means this or this. Whatever. In both the CDs, you can find that the Reynolds number is involved. And the Reynolds number is again velocity into diameter to density of the fluid by dynamic viscosity. Again here, the velocity is again involved. Very clear. That means to find a velocity, we need to know the velocity again. So it is quite a contradictory statement, right? Our objective is to find the settling velocity of the particle. We don't know whether it is transitional or we don't know whether it is laminar. Even though we don't know, we just try to assume either laminar or transitional. But in both the terminology, the CD value is 24 by Re or plus addition of this 3 by Re plus 0.34. But the Reynolds number again involves the terminology, the settling velocity again. So to find the settling velocity, we have to know the velocity again. So it is quite continuous reaction. It is never ending. It is cyclic. It's a loop. To find 1, you have to find 2. To find 2, you have to find 10. To find 10, you have to find 12. To find 12, you have to find 1. So it's a cyclic like a clock. Okay. So we are confused from where we have to start. The reason I'm explaining this so that you will never forget how to start a problem, because this question always also comes either derivation or the numericals in many of the exams. And this question may come for the maximum of 30 marks in sectional officer examination of engineering. Otherwise, it may be 50 to 20 marks. So what we do is, straight away, we use this equation. But this is laminar flow. So another example, I'll give again. To find this one, you have to find 3. To find the 3, you have to find 6. To find 6, you have to find 9. To find 9, you have to find 1. So we don't know from where to start. So what we will do is, straight away, we'll start somewhere from here. Okay, that is settling velocity. So straight away, first, we'll assume that the flow is laminar. Listen first, I'll solve the problem. We'll assume that the flow is laminar, and directly we'll use this equation. In this equation, D is given diameter, density is there, or specific gravity, dynamic viscosity of the fluid, it has to be given, and G acceleration due to gravity is given. So straight away you can find the settling velocity. Is that clear? Very simple. But the problem is, we also use this by doing certain assumption that the flow is laminar. So now, after using this as Stokes law, we penetrate the cycle. We have to check whether the flow is really laminar or not. So since we have a settling velocity, we will find the Reynolds number. Okay, so this is going to be step number 1, and this is going to be step number 2. We will see whether it is Reynolds number. So finding the Reynolds number, the settling velocity is already found out, D is there, density is there, mu is there. We'll find the Reynolds number, and then we'll check whether then number 3 is, we'll find the CD value. Okay. So by knowing the Reynolds number, we can check whether the flow is laminar or transitional. As I explained last class, if it is less than 1, it is laminar. It's in range little bit greater than 1, then it is transitional. Correct? So now let me repeat again, so that you don't have to rewind with you. First of all, we will straight away find step number 1, that is settling velocity using Stokes law, assuming that it is laminar flow. Getting the settling velocity, we will find out what is Reynolds number, and we will check whether the flow is laminar or transitional. If it happens to be less than 1, then it is laminar. Then the answer is over. Settling velocity is correct. But if it doesn't come to be laminar, then if the Reynolds number is greater than 1, then we have to find a value of CD. So it is transitional, CD value means this value. And then using the CD equation, we have to find out by using this equation. Because CD is already over here. So settling velocity we will use with this terminal velocity equation. Is that clear? Fine. Now let me rub it off and let me start solving the problem. Okay. So for this equation, I told you, number one, certain velocity is equal to 1 by 80 g 9.8 d square 0.5 into 10 to the power minus 3 square. This is because we have to make in terms of meter assignments. Then density minus density of the water. Now here, density, since the specific gravity is 2.65, density will be 2650. Simple. I'll just write and I'll rub it off. Specific gravity is equal to density of the particle by density of the water. So density of the particle is equal to specific gravity into density of the water. 2.65 into 1000 is equal to 2650. Is that okay? Fine. So this value we are using here. I missed another point over here. That here the density of the fluid that we are using, it may be 981 kg per meter. What happened is, actually the density of the water happens to be 1000 kg per meter cube. But since it is not a pure water, due to some certain, what do you call this, impurities, the density is this question, okay? So this is fine. So now what we do is, this 2650 minus 981 divided by the dynamic viscosity, that is 1.002 into 10 to the power minus 3 Newton second per meter square. So by using the calculator, you have to solve this equation, and what we got is 0.22 meter per second. This is step number one. Is it clear? We got the second velocity as 0.22 meter per second. Now we have to check. Number two step is check Reynolds number. So RE is equal to velocity into diameter into density divided by mu. And remind you, my dear students, always whenever you write steps, you always include the formula. This way it will be very, very difficult for you to forget the formula even. Otherwise, even the faculty will think you are copying from your friends. So always mention the formula. So by using this formula, velocity is 0.22 into diameter is 0.5 into 10 to the power minus 3. And the density is 981 divided by 1.002 into 10 to the power minus 3. Okay. And Reynolds number what we get is 112. But this is greater than 1. So what happened is, this is transitional flow. Okay. So first step is identifying this one by using Stokes law. Second is check the Reynolds number. So on doing this, we came to know that the second velocity is 0.22 meter per second, but the Reynolds number happens to be 112. That is, the flow is conditional. It is not a laminar. Therefore, this second velocity is not exactly correct. How to rectify it? It'll be the next step. Okay. Now, the third step is you have to find what is CD value. CD is equal to 24 by RE plus 3 by root over RE plus 0.34 is equal to 24 by 112 plus 3 by root over 112 plus 0.34. By using calculator, you'll find it is 0.84. Okay. So CD, you are having this. Why are we finding CD? This is completely one cycle. Now I'll wipe here. This is completely one cycle is all. Now, second cycle. Settling velocity we have to find not by using the Stokes law, since it is transitional, but by using the terminal velocity formula. Settling velocity is equal to square is equal to 4 by 3 g d s minus 1 divided by c. Okay? So here is equal to 4 by 3 into 9.81 into 0.5 into 10 to the power minus 3. So S minus 1 is not 2.65 minus 1 because the density of the water given is not 1000 but 91. So what we can do is, here is 2650 minus 981 divided by 981. Okay. Divided by the CD value, 0.84. Okay. And this settling velocity, you got it as 0.11 meter per second. Settling velocity, not a square. This is completely a settling velocity. I think, let me come back again. The first step is find the settling velocity using the laminar equation, using the Stokes law equation. Then check the Reynolds number. It is more than transitional. Therefore, you have to find the CD, and CD is equal to 0.84. Here, the first cycle is over. And in second cycle, we straight away use the terminal velocity formula we had derived yesterday. So it is, the value happens to be, using the CD value, the settling velocity happens to be 0.11 meter per second. Now, the thing is, in this second cycle, are you very sure that the settling velocity of 0.11 meter per second will be transitional, or it may go to turbulent also? Or even if it is transitional, the value of the CD may be different. Okay, so let me drop this part. And after finding the settling velocity, the second steps for the second cycle, that is, you have to find again the Reynolds number is equal to settling velocity into diameter into density divided by dynamic viscosity. Is equal to settling velocity is 0.11, the new one, into diameter is 0.5 into 10 to the power minus 3 meter. Okay, into density 981 kg per meter cube, and dynamic viscosity is 1.002 into 10 to the power minus 3 Newton second per meter square. So the second Reynolds number is, you got it as 55. See, the first Reynolds number we used to get as 112. Now Reynolds number is reduced to 55. So based on the Reynolds number, again we have to find CD value. CD is equal to 24 by RE plus 3 by root over RE plus 0.34 is equal to 24 by 55 plus 3 by root over 55 plus 0.34, and you will get the value of 1.13. That is a CD value. Okay. So here in the first cycle, we got CD is equal to 0.84. In the second cycle, we got CD is equal to 1.13. But one thing is common, the flow is transitional because the Reynolds number in the previous is 112, now it is 25. Then still, this is transitional. Okay. Even though the flow is transitional, you have to check because the Reynolds number decrease, the CD value decrease. So now we have done 2 cycles of hit and trial. Fine. We have done 2 cycles of hit and trial. Is it okay? So now let me go for the third cycle. Now, third, I'll say iteration. Third iteration means hit and trial. Okay, third cycle. First, you find settling velocity. Again, by using terminal velocity, that is 4 by 3 GD S minus 1 by CD. So 4 by CD into 9.8. D is 0.5 into 10 to the power minus 3 meter into S minus 1. Now you can put 2.65 minus 1 divided by CD. CD means 1.13. Okay, fine. Now this settling velocity. Remember here, this is square, this is S. That means we are taking root of. Okay. So settling velocity comes to 0.10 meter per second. This is the third iteration, settling velocity. Is it clear? Fine. This is the third iteration. Now, using this equation again, the next step is again find Reynolds number. RE is equal to velocity into diameter into density divided by mean. And this velocity will be 0.10. Okay? 0.10. And then next cycle is you find CD. And this value will be again in the transitional mode. So CD is equal to 24 by RE plus 3 by over RE plus 0.34. Then you find again the settling velocity using terminal velocity. Now the question comes, sir, how many cycles are we supposed to do? How many times are we supposed to do the iteration technique? Right? Our ultimate aim is to find the settling velocity, this value, and the next value, and every round of settling velocity. So every round we are finding settling velocity. Settling velocity in the round 1, round 2, round 3, round 4, round 5. Okay. Now let me put it here. So settling velocity 1, we got 0.22 meter per second. Settling velocity 2, we got 0.11 meter per second. Settling velocity number 3, we got 0.10 meter per second. Settling velocity number 4, which we are supposed to estimate, this will be around 0.09 meter per second. Now, the thing is, we can say that comparing with all these values, here these values are very, very close. Here it is far. Am I correct? The moment the settling velocities in every iteration or in every cycle comes very, very close, we can say since Vs3 is close to Vs settling velocities, cycle number 4, settling velocity is equal to Vs3, it's equal to 0.10 meter per second. So this is the final answer. Or sometimes Even you can mention these two are also very close, so settling velocity is 0.11 also you can consider. There is not a problem. But my point is, actually, you are not a computer engineer right now, you are still a student, and we want to check your basic fundamentals during exam time. So we want to know whether you have the fundamentals of solving this equation or not by different iterations. Clear? That's all. So I'm giving you 1 minute. After that, let me repeat the experiment again as per the feedback of some few students who said, sir, please kindly repeat it again. Okay? Fine. Now, summarizing, let me tell you one thing. Number one is, first, directly find settling velocity using Stokes law or Stokes equation. That is, Vs is equal to 1 by 18 Gd square rho p minus rho w divided by mu. Okay? Mind you, I have solved this equation many times that even after derivation or even without derivation, I have remembered this equation. It's also very, very important. In the exam time, they may not ask you the derivation, but they may ask you. So if you don't remember this formula again, you have to derive from the beginning again. Okay? Number two, check Reynolds number, and that is Re is equal to settling velocity into diameter into density, diameter into density divided by mu, and check laminar or transition. Okay. Number three is, if it is laminar, the story stops. If this is laminar, the story stops, and then the settling velocity is this, finished. But if this is transitional, then you have to find C is equal to 24 by Re plus 3 by root over Re plus 0.34. Okay, now here one iteration is completed. Iteration 1 is complete. So you have to repeat the cycles again and again. So next cycle is again 1. Second cycle. You can find settling velocity, but this time the settling velocity is not a Stokes law. It should be the terminal velocity formula. There is 4 by 3 G D is minus 1 divided by CD whole root over. I'm not putting square. I'm doing different style to make you confused purposely. Okay. So by using the settling velocity, number 2, you have to check again Reynolds. Then you have to find CD. Is that fine? And you have to end the iteration technique when you find two settling velocity very, very close to each other, and that value is a settling velocity. The ultimate objective is find close value of velocity settling, and that is the settling velocity. Fine. I think I have done repeatedly explaining again and again. The video will be unnecessarily lengthy. So till now I have done the derivation and this one itself. But don't expect that in the exam I'll ask straight away this way. Is that okay? Clear? So I'm closing this video, and now through WhatsApp I'll be sending you a question not for 0.05, or I will say you find the settling velocity of 0.02 mm. You do this question and you submit it. Write in a piece of paper, submit through WhatsApp. Okay. Find the settling velocity of these particles. Find. And at 20 degrees centigrade, dynamic viscosity is equal to 1.002 into 10 to the power minus 3 Newton second per meter square. Is that okay? You solve me, and specific gravity is 2.65, and submit the assignment. Okay. Now, let me give you a twist. Now, in case if the question comes in kinematic viscosity, okay, then what we are supposed to do? Remember, what we have to remember is equal to dynamic viscosity divided by density. Is that okay? Fine. So whenever you use the equation terminal velocity, this will be, sorry, I mean to say Reynolds number, Reynolds, so the velocity into diameter into density divided by mu. This will be what? Velocity into diameter divided by 2. Okay? And settling velocity Stokes is equal to 1 by 18 g d square s minus, sorry, rho p minus rho w divided by mu. This will be, if mu, what we can do is mu by rho will be mu. So what we'll do is we'll put one mu, we'll put one rho here, and we'll put one rho here. Okay? So this divided by this will be mu. So it will be 1 by 18 g d square rho p minus rho by rho. This will be rho p minus rho w divided by rho, and this will be. Is that okay? Or this is equal to 1 by 18 g d square s minus 1 divided by mu. Okay? I think the concept is clear. If you have any doubts during the Monday class, again, I'll try to explain if you have any doubt. It is just a calculation of mu and mu, dynamic and kinetic viscosity. Okay, my dear students, have a glance. I'll try to switch off the camera. Thank you.